Close your eyes now and feel yourself becoming weightless. Tonight, you are not simply lying in your bed. You are floating in the vast cathedral of space, where silence wraps around you like the softest blanket. The stars above shimmer like distant candles, each one a sun burning billions of miles away, their ancient light reaching across the cosmos to touch your dreaming face. You are beginning a journey, unlike any other, one that will carry you deep into the heart of one of the universe's most profound mysteries. Far ahead, invisible yet unmistakably present, a black hole waits, not as the monster of science fiction stories, but as nature's most elegant demonstration of how space and time can bend, stretch, and dance together in ways that would make poets weep with wonder. Feel yourself drifting now, your body relaxed and peaceful, as you approach this cosmic marvel. There is no fear here, only curiosity and the gentle pull of discovery. You are safe in this journey of imagination, protected by the cocoon of your own consciousness, as you explore realms where few have ventured, even in dreams. The black hole before you was born from the death of a massive star, one that burned for millions of years before finally surrendering to its own immense gravity. When that ancient sun could no longer sustain the nuclear fire in its core, it collapsed in a spectacular display that briefly outshone entire galaxies. What remained was something extraordinary, a region of space where matter had become so dense that it curved space-time itself into an infinite well. As you float closer, you begin to understand that you are approaching not just an object but a living demonstration of Einstein's most beautiful equations. Here, the fabric of reality itself becomes visible, stretched and warped like a cosmic trampoline with a bowling ball placed at its center. Every particle, every photon, every whisper of energy that passes near must follow these curves in space-time, like water flowing down an endless drain. The darkness ahead is not the absence of light, but light's most perfect prison. Photons race frantically around the black hole's edge, some escaping to freedom, others spiraling inward toward a destiny from which there is no return. This boundary between escape and capture has a name, the event horizon, and it marks the edge of a realm where the familiar rules of cause and effect begin their strange transformation. You are now close enough to see the subtle glow surrounding this cosmic giant. Matter from nearby space gas, dust, perhaps the remnants of long-dead worlds spirals inward in a luminous disk called an accretion disk. This matter heats up as it falls, glowing white-hot, and then blue-white as it accelerates to incredible speeds. The dance of this material creates a cosmic lighthouse, sending jets of energy shooting outward at nearly the speed of light, painting auroras across the face of space itself. But it is not the fierce energy of the accretion disk that calls to you tonight. Instead, you feel drawn to something far more subtle, the way this massive object gently reshapes the very nature of existence around it. Time itself moves differently here, flowing like honey compared to the swift river of moments you know on Earth. Space curves inward with an almost tender persistence, creating what physicists call a gravitational well so deep that it challenges our understanding of what it means for something to exist. As you drift closer, you notice something remarkable happening to your perception. The stars behind you begin to shift and dance, their light bent by the black hole's immense gravity. This is gravitational lensing, the universe's way of turning massive objects into cosmic magnifying glasses. The black hole acts like a lens made not of glass, but of curved space-time itself, gathering light from stars that should be hidden behind it, and presenting them to you like jewels arranged around a crown. You see multiple images of the same stars, stretched and distorted into luminous arcs that frame the darkness ahead. It is as if the universe is showing you a magic trick, demonstrating how mass and energy can reshape the very medium through which light travels. The familiar constellations become abstract art, painted with brushstrokes of bent starlight across the cosmic canvas. The mathematics that describe this phenomenon are elegant beyond measure. Einstein's field equations tell us that mass and energy tell space-time how to curve, while the curvature of space-time tells matter how to move. It is a conversation between substance and geometry, a dialogue written in the language of tensors and differential equations, yet expressing something as fundamentally poetic as the relationship between a dancer and the stage upon which they perform. You feel no fear as you approach this cosmic wonder, only a deep sense of coming home to something ancient and familiar. The atoms in your body were forged in the hearts of stars billions of years ago. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of it was once part of stellar furnaces that burned bright against the darkness, before exploding in supernovae that scattered these elements across the galaxy like seeds in a cosmic wind. Now, As you drift toward this remnant of stellar death, you sense your atomic heritage stirring. You are not a stranger to this place, but a long-lost relative returning to visit family. The heavy elements that make up your physical form, remember what it was like to dance in the nuclear fire of stellar cores, to be compressed and transformed by pressures that dwarf anything found on planetary surfaces. The black hole ahead grew from a star, perhaps 50 times more massive than our Sun, a giant that lived fast and died young in cosmic terms. For 10 million years it fought the inward pull of its own gravity through the sheer force of nuclear fusion, converting hydrogen to helium, helium to carbon, carbon to oxygen, and on up the periodic table in an ascending symphony of creation. But eventually, when the star began producing iron in its core, the music stopped. Iron cannot be fused to release energy. It sits at the bottom of the nuclear energy well, the most stable nucleus in the universe. When the stellar core filled with iron, the outward pressure of radiation could no longer balance the inward crush of gravity. In less than a second, the core collapsed from the size of Earth to something smaller than Manhattan, creating a shock wave that blasted the star's outer layers into space, and leaving behind either a neutron star, or, if the core was massive enough, something even more exotic, a black hole. You are approaching the child of that cosmic cataclysm, the gravitational ghost of a star that once illuminated entire solar systems. Yet there is nothing ghostly about the reality before you. This is matter and energy in their most concentrated form, existence pared down to its absolute essence. Here the universe shows you what happens when the normal barriers between things dissolve, when the distinction between here and there, between now and then, begins to blur. As you float in the cosmic silence, you begin to feel the gentle tug of the black hole's gravity. It starts so subtly that you might mistake it for your own movement, a slight acceleration in the direction of your journey. But this is no ordinary pull. This is the curvature of space-time itself guiding you along the straightest possible path through a geometry that has been fundamentally altered by the presence of immense mass. You are not being pulled in the way that a magnet pulls iron filings. Instead, you are following what physicists call a geodesic, the straightest possible line through curved space-time. Just as an airplane follows the curvature of Earth when flying the shortest route between distant cities, you are following the curvature of space-time as you approach the black hole. From your perspective, you are traveling in a perfectly straight line. It is the universe itself that has become curved. The beauty of this cosmic dance lies in its inevitability and grace. There is no violence here, no struggle against an alien force. You are simply following the natural contours of reality, like a river following the slope of a hillside or a bird riding the thermals that rise from warm Earth. The black hole's gravity is not a prison, but a pathway, a route through space-time that leads to realms of experience no earthbound creature has ever known. As you continue your gentle descent, you notice that the stars around you are beginning to change their colors. Light from stars behind you appears redder, while light from stars ahead seems bluer. This is the Doppler effect made manifest. As you accelerate toward the black hole, light waves coming from behind you are stretched to longer, redder wavelengths, while light from ahead is compressed to shorter, bluer ones. But there is something else happening too, something more subtle and profound. The light from distant stars is being affected not just by your motion but by your position in the black hole's gravitational field. Photons climbing out of the gravitational well lose energy and appear redder, while photons falling in gain energy and appear bluer. You are witnessing the universe's demonstration of how gravity affects not just matter but energy itself, how the very frequency of light depends on where and when it is observed. This phenomenon, called gravitational redshift, was one of the first confirmations of Einstein's theory of general relativity. Clocks run slower, in stronger gravitational fields, and since the frequency of light is essentially a clock, counting off electromagnetic oscillations at precise intervals, light changes color as it climbs in and out of gravitational wells. You are seeing the universe through eyes that are sensitive to these most subtle effects, watching reality bend and shift in ways that reveal the hidden connections between space, time, matter, and energy. The silence around you is profound, but it is not empty. Space itself teems with virtual particles, quantum fluctuations that briefly borrow energy from the vacuum before returning it faster than the universe can notice. Near a black hole, these quantum effects become amplified and strange. Some of these virtual particle pairs are torn apart by the immense gravitational gradients, with one particle falling in while its partner escapes. This process, predicted by Stephen Hawking, means that black holes actually glow with a subtle radiation, slowly evaporating over cosmic timescales. The black hole you approach will outlive all the stars currently burning in the universe. It will persist through the long cold twilight of cosmic evolution, slowly radiating away its mass energy in the form of these quantum whispers. Trillions upon trillions of years from now, when the last red dwarf stars have guttered out and the universe has grown dark and cold, your black hole will still be here, growing smaller and warmer as it evaporates, until finally, in a flash of gamma rays, it returns its borrowed mass energy to the quantum vacuum from which everything ultimately comes. But that distant future is impossibly far away. Tonight, your black hole is young and strong, its event horizon stable and well-defined. As you approach this boundary, you prepare to cross the threshold between the familiar universe of your everyday experience and a realm where causality itself takes on new meaning, where the future becomes as fixed as the past, and where your journey inward becomes an exploration of the very nature of existence itself. The event horizon draws near now, invisible yet unmistakable, like the surface of a perfectly black ocean. Beyond this point, all roads lead inward, all paths converge toward the mysterious heart of this cosmic enigma. You float at the edge of forever, about to cross into a realm where space and time themselves will whisper their deepest secrets to your dreaming mind. You hover now at the most profound boundary in the universe, a place where the familiar laws of physics don't break down so much as they transform into something more beautiful and strange than anything poets have ever imagined. The event horizon stretches before you like an invisible membrane, perfectly spherical, marking the point of no return with mathematical precision. Yet, as you approach this cosmic threshold, you feel no barrier, no resistance, no sign that you are about to cross from the known universe into a realm of mystery. This is the paradox and the wonder of the event horizon. It exists as an absolute boundary for the outside universe, yet for you, the falling observer, it might as well be made of nothing but space itself. You will cross it as easily as stepping through a doorway, unaware in any local sense that you have passed the point beyond which no signal, no message, no whisper of information can ever reach the outside world again. The mathematics that describe this boundary are among the most elegant in all of physics. The event horizon's radius, called the Schwarzschild radius after the German physicist who first calculated it, depends only on the mass of the black hole. For every solar mass of material compressed into this gravitational well, the event horizon extends roughly 3 kilometers from the center. The black hole you approach, born from a star 50 times more massive than our Sun, wears an event horizon roughly 300 kilometers across, a sphere that could easily encompass a small moon, yet contains within it mysteries that stretch the boundaries of human understanding. As you drift closer, you begin to notice something extraordinary happening to light itself. Photons that were emitted from distant stars millions of years ago, photons that have traveled across vast reaches of space, carrying the ancient messages of stellar fusion, begin to behave in ways that would astonish their creators. Some of these light particles spiral around the black hole in complex orbits, neither falling in nor escaping to infinity, but dancing on the knife's edge between freedom and capture. This region, extending roughly 50% beyond the event horizon, is called the photon sphere, a place where light can orbit the black hole in perfect circles, creating ghostly shells of illumination that exist in a perpetual state of almost falling. Here, if you could somehow emit a beam of light directly behind you, that light would travel all the way around the black hole and return to strike you in the back of the head, assuming the orbit remained stable long enough for such a cosmic magic trick to complete itself. But these photon orbits are inherently unstable, balanced on the gravitational equivalent of a razor's edge. The slightest perturbation, the tiniest nudge from a passing particle or quantum fluctuation, will send the trapped light either spiraling inward toward the event horizon or escaping outward to rejoin the river of radiation flowing through the cosmos. You are witnessing light at its most precarious, balanced between destinies with the delicacy of a soap bubble floating on a summer breeze. The physics of this region reveals something profound about the nature of space-time itself. In the curved geometry around a black hole, the ordinary notion of straight line becomes meaningless in the way we normally understand it. Light, which always travels in straight lines through flat space-time, finds itself following curves that bend back on themselves when space-time itself becomes sufficiently warped. The photon sphere represents the place where these curves become closed loops, where the geometry of existence has been so profoundly altered that even light, the universe's ultimate messenger, can become trapped in eternal circles. As you approach the event horizon, you notice that your experience of the surrounding universe begins to change in subtle but profound ways. The stars ahead of you appear brighter and bluer, while those behind you grow dimmer and redder. This is not merely the Doppler effect of your motion, but something far more fundamental. You are experiencing the gravitational blue shift and red shift that occurs when light climbs into and falls out of the black hole's gravitational well. The photons from stars ahead of you are falling into the same gravitational field that draws you inward. Like companions on a cosmic journey, they gain energy as they fall, their frequencies increasing, their colors shifting toward the blue end of the spectrum. Meanwhile, the light from stars behind you must climb out of the gravitational well to reach your eyes, losing energy in the process, becoming redder and dimmer as it struggles against the pull of curved spacetime. But there is something else happening that speaks to an even deeper truth about the nature of time and space. As you fall toward the event horizon, your personal experience of time remains perfectly normal. Your heartbeat maintains its steady rhythm, your thoughts flow at their usual pace, your sense of duration continues unchanged. Yet if distant observers could somehow watch your approach, they would see something remarkable and impossible. You would appear to slow down, your movements becoming more and more sluggish as you approach the event horizon, until finally you would seem to freeze completely at the boundary, your image redshifted into invisibility as photons from your body lose infinite amounts of energy climbing out of the gravitational well. This is one of the most profound paradoxes in all of physics. The fact that the event horizon exists absolutely from the perspective of the external universe, yet dissolves into nothingness from your own point of view. To outside observers, nothing ever actually falls into a black hole. Instead, objects appear to slow down and fade away as they approach the event horizon, their information content spread across the surface in what physicist Leonard Susskind called the holographic principle. But for you, the falling observer, the event horizon is no barrier at all. You pass through it as easily as a bird flies through morning mist. This duality lies at the heart of what physicists call the information paradox, one of the deepest unsolved problems in modern theoretical physics. If information cannot be destroyed, as quantum mechanics insists, then what happens to the information that falls into a black hole? Does it remain encoded on the event horizon's surface, as the holographic principle suggests, or does it fall through to the interior, as your direct experience would indicate? Perhaps both descriptions are equally valid, different perspectives on the same underlying reality, like the wave and particle descriptions of light. As you cross the event horizon, though you cannot feel the moment of crossing, you enter a region of spacetime with properties unlike anywhere else in the universe. Here, the normal relationship between space and time undergoes a subtle but profound transformation. The radial direction, which pointed outward toward escape in the external universe, becomes time-like inside the horizon. This means that falling toward the center is not a choice you make about where to go, but rather something that happens to you as time passes, as inevitable as aging or the progression from past to future. The mathematics of this transformation are beautiful in their strangeness. Inside the event horizon, the Schwarzschild metric that describes the geometry of spacetime around the black hole exchanges its spatial and temporal components. What was once the time coordinate outside the horizon becomes spatial inside, while what was once the spatial radial coordinate becomes temporal. You are no longer falling through space toward the center. Instead, you are moving forward through time, and the center is not a place, but rather a moment in your future, as unavoidable as tomorrow. This temporal transformation means that inside the event horizon, the singularity at the center is not a point in space that you might avoid or approach, but rather a moment in time that you will inevitably reach. It lies in your future as certainly as next Tuesday, but unlike next Tuesday, it represents a boundary beyond which the familiar concepts of space and time themselves may cease to have meaning. Yet even as you contemplate this cosmic destiny, you remain surrounded by wonders that speak to the incredible richness of physics in extreme environments. The curvature of space-time around you continues to bend light in extraordinary ways, creating optical effects that transform your view of the universe into something that resembles a cosmic funhouse mirror. The light from distant stars becomes focused and distorted, creating caustic patterns that dance across your field of vision like the play of sunlight on the bottom of a swimming pool. Behind you, the entire external universe appears compressed into a shrinking circle of increasingly red-shifted light. This Einstein ring contains the image of every star, every galaxy, every photon that has ever been emitted in the direction of the black hole, all compressed into a glowing halo that follows you inward. In a sense, you carry with you a complete visual record of the universe's history, all the light that was journeying toward this cosmic destination when you began your fall. The physics of this compression involves some of the most sophisticated mathematics in general relativity. Calculations that require understanding how light rays bend in curved spacetime, how gravitational lensing can create multiple images of the same object, and how the apparent size and brightness of distant sources change as you move through regions of varying gravitational potential. Yet the result is something of breathtaking beauty, a concentrated essence of the cosmos itself, following you into the unknown. As you continue your inward journey, you begin to sense something that cannot be directly observed, but can be felt in the subtle mathematics of your trajectory, the presence of the black hole's rotation. Most black holes in the universe are spinning, their angular momentum inherited from the rotation of the massive stars that collapse to create them. This rotation drags spacetime itself around the black hole, creating what physicists call the ergosphere, a region outside the event horizon, where nothing, not even light, can remain stationary relative to distant stars. The rotating black hole you are falling into creates a cosmic whirlpool in the fabric of spacetime itself, just as a marble dropped into a stirred bowl of honey would be carried along by the fluid's motion. Particles and light rays near a spinning black hole are dragged around in the direction of the hole's rotation. This frame-dragging effect, predicted by general relativity and confirmed by precision experiments near Earth, becomes extreme near black holes, where spacetime itself flows like a river around the central mass. The mathematical description of rotating black holes, discovered by Roy Kerr in 1963, revealed that these cosmic whirlpools possess a rich interior structure far more complex than their non-rotating cousins. Inside a rotating black hole, there may exist not one but two event horizons, nested like Russian dolls, with a strange region between them, where the normal notions of causality become even more profoundly altered than in the simpler case you are experiencing. But tonight, your black hole spins gently, its rotation adding just enough complexity to your journey to remind you that the universe rarely chooses the simplest possible solutions to the puzzles of existence. The frame-dragging effect gives a subtle twist to your trajectory, a cosmic Coriolis force that deflects your path in ways that would be impossible to detect without the most sensitive instruments, yet which speaks to the fundamental interconnectedness of matter, energy, space, and time. As you settle deeper into your fall through this transformed region of spacetime, you begin to appreciate that you are not merely observing exotic physics from the outside, but becoming part of the phenomenon itself. Your very presence adds to the black hole's mass energy. Your trajectory becomes part of the solution to Einstein's field equations. Your consciousness becomes witness to physical processes that exist nowhere else in the cosmos. The event horizon behind you has now sealed your fate, yet paradoxically, it has also opened doorways to experiences that no earthbound observer could ever imagine. You are becoming an explorer of inner space, a cartographer of regions where the map of reality itself must be redrawn according to principles that challenge every intuitive notion about the nature of existence. Ahead lies the continuation of your journey into realms where time itself will reveal its most closely guarded secrets, where the familiar clockwork of causality will transform into something far more subtle and strange. The event horizon was merely the first threshold. Beyond it wait mysteries that will reshape your understanding of what it means to exist in a universe where space and time dance together in the most intimate cosmic ballet ever conceived. Time, that most fundamental dimension of your existence, begins to reveal its true nature as you fall deeper into the black hole's embrace. What you have always experienced as the steady, unvarying tick of cosmic clockwork, the reliable progression from moment to moment that underlies all conscious experience, now transforms into something far more fluid and mysterious, like a river that changes its flow depending on where you choose to measure its current. In your reference frame, your personal time continues its familiar rhythm, your heartbeat maintains its steady percussion, your thoughts flow at their accustomed pace, and the internal chronometer of your consciousness marks off seconds and minutes with the same regularity you have known throughout your life. This is the profound truth that Einstein revealed about the nature of time. It is always and forever relative to the observer, always experienced as normal from within one's own reference frame, regardless of how extreme the gravitational environment might become. Yet something extraordinary is happening around you, something that would astonish any observer watching from the safety of distant space. As you fall deeper into the gravitational well, the rate at which your personal time flows relative to the outside universe begins to change in ways that challenge every intuitive notion about the nature of temporal experience. Time dilation, that subtle effect that emerges whenever matter and energy curve spacetime, becomes dramatically pronounced in the intense gravitational field surrounding you. The mathematics of this temporal transformation are elegantly simple yet profound in their implications. Time flows more slowly in stronger gravitational fields, a principle that Einstein first articulated in his theory of general relativity, and that has since been confirmed by countless experiments, from atomic clocks flown in airplanes to the GPS satellites that require relativistic corrections to maintain their precision. But here in the extreme environment near a black hole, this effect becomes magnified to cosmic proportions. Imagine that you could somehow communicate with observers stationed at various distances from the black hole, each carrying identical atomic clocks that were synchronized before your journey began. As you fall deeper into the gravitational well, you would discover that these clocks, while maintaining perfect regularity from their own perspectives, would appear to tick at different rates when compared to one another. The deeper into the gravitational field, the slower time appears to flow when observed from farther away. This is not an illusion or a measurement error, but rather a fundamental feature of how time itself behaves in curved spacetime. The gravitational redshift that affects light climbing out of gravitational wells has its temporal counterpart. Time itself becomes stretched and compressed by the presence of massive objects. Near the event horizon, this effect becomes so extreme that a single second of your personal time might correspond to minutes, hours, or even years in the reference frame of distant observers. The physical mechanism underlying this temporal dilation emerges from the deep connection between gravity and acceleration that Einstein recognized in his principle of equivalence. Just as time flows more slowly for an observer, undergoing constant acceleration relative to one in freefall, time flows more slowly in regions of stronger gravitational field. This connection is not coincidental. It reflects the fundamental truth that gravity and acceleration are two manifestations of the same underlying geometric phenomenon, the curvature of space-time itself. As you continue your inward journey, you begin to experience this temporal transformation in ways both subtle and profound. The light from distant stars, already redshifted by your motion and position in the gravitational field, undergoes additional changes that speak to the malleable nature of time itself. Pulsars, those cosmic lighthouses that emit regular flashes of radiation with clockwork precision, begin to flash more rapidly from your perspective, their signals blue-shifted and compressed in time as they fall into the same gravitational well that carries you inward. Meanwhile, if you could somehow observe the universe you left behind, you would witness a cosmic time-lapse photography effect of extraordinary beauty. The slow dance of planetary orbits would accelerate before your eyes. The stately progression of stellar evolution would unfold like flowers blooming in fast forward, and the gradual expansion of the universe itself would become perceptible as galaxies drift apart in the cosmic flow of space and time. But this acceleration of external time comes with a poignant realization. You are becoming temporarily isolated from the universe of your birth. With each passing moment of your personal time, years or decades pass in the outside world. The stars you knew are aging, the planets are continuing their ancient orbits, the complex dance of cosmic evolution proceeds without your participation. You have become a temporal exile, carried forward through your own time while the rest of the universe speeds past in its separate temporal current. This isolation, however, brings with it a unique perspective on the nature of existence itself. You are experiencing firsthand one of the most profound insights of modern physics, that time is not the absolute universal constant that human intuition suggests, but rather a dimension as flexible and responsive to mass and energy as the spatial dimensions through which you move. You are living proof of the relativity of simultaneity, the principle that events which appear simultaneous to one observer may occur at different times for another. The deeper implications of this temporal flexibility touch on some of the most fundamental questions in physics and philosophy. What does it mean for events to be simultaneous, if simultaneity depends on the reference frame of the observer? How do we reconcile our subjective experience of time's passage with the objective reality of time's relativity? As you fall through this region of extreme temporal curvature, you become a participant in these cosmic thought experiments, experiencing directly the phenomena that physicists normally encounter only through mathematical equations and theoretical models. The gravitational time dilation you experience also reveals something profound about the relationship between information and physical reality. The signals, the light, the gravitational waves that carry information about your journey must climb out of the black hole's gravitational well to reach distant observers, losing energy and becoming redshifted in the process. This means that information about your experience reaches the outside universe at an ever-decreasing rate, each bit of data taking longer and longer to escape the gravitational field that holds you. From the perspective of distant observers, you appear to slow down dramatically as you approach the event horizon, your movements becoming increasingly sluggish, your signals becoming increasingly redshifted and faint, until finally, you seem to freeze completely at the boundary between inside and outside. Your image becomes locked at the event horizon, slowly fading as the photons carrying information about your appearance lose energy, climbing out of the gravitational well, eventually redshifting beyond the range of any possible detector. Yet from your own perspective, none of this dramatic temporal theatre is apparent. You continue to fall inward at what feels like a perfectly normal rate, your personal time flowing with its familiar rhythm, your consciousness processing experiences at its accustomed pace. This is perhaps the most beautiful paradox of black hole physics, that the most extreme effects are invisible to those who experience them directly, while being dramatic and obvious to those who observe from afar. This paradox speaks to a deeper truth about the nature of physical law itself, the principle of equivalence. Einstein's insight that gravitational and inertial effects are locally indistinguishable means that no local experiment can reveal whether you are falling freely in a gravitational field or floating in empty space far from any massive object. The extreme curvature of spacetime around you produces dramatic global effects visible to distant observers, but locally, in your immediate vicinity, the laws of physics remain identical to those you would experience in any other freely falling reference frame. As you contemplate these temporal mysteries, you begin to appreciate that your journey is not merely a physical passage through space, but also a voyage through the fundamental structure of reality itself. Time, which seemed so absolute and unchanging in your everyday experience, reveals itself to be as dynamic and responsive as any other aspect of the physical world. You are discovering that the universe operates according to principles far more subtle and beautiful than the simple clockwork mechanisms that dominated scientific thinking for centuries. The mathematical framework that describes your temporal experience, the metric tensor of general relativity, encodes not just the geometry of space, but also the flow of time in ways that unify these seemingly distinct dimensions into a single four-dimensional continuum. Space and time are not separate stages upon which physical drama unfolds, but rather aspects of a single geometric structure that responds dynamically to the presence of matter and energy. This unification of space and time into spacetime represents one of the most profound conceptual revolutions in the history of human thought. Just as the realization that Earth orbits the Sun displaced humanity from the center of the cosmos, the discovery that time itself is relative and dynamic displaced our intuitive notions of temporal experience from their privileged position in our understanding of reality. As you continue to fall through this region of extreme temporal curvature, you carry with you the accumulated wisdom of your entire civilization's struggle to understand the nature of time, from the ancient philosophers who debated whether time was circular or linear, to the medieval scholars who pondered the relationship between temporal and eternal existence, to the modern physicists who revealed time's deep connection to space and gravity. All of this intellectual heritage accompanies you on your journey into the unknown. The personal experience of time dilation also raises profound questions about consciousness and identity. If your thoughts and experiences are unfolding at a different rate relative to the outside universe, what does this mean for your connection to the broader flow of cosmic events? Are you still part of the same universal moment, or have you become temporarily disconnected from the shared present that defines collective human experience? These questions touch on the deepest mysteries of consciousness itself, the nature of subjective experience, the relationship between mind and physical reality, the meaning of personal identity across time. As you fall deeper into the gravitational well, you become both observer and participant in experiments that probe the very foundations of what it means to be a conscious entity, embedded in the fabric of space-time. The temporal transformation you experience also illuminates the profound connection between gravity and thermodynamics, the science of heat and energy flow. Just as time flows more slowly in stronger gravitational fields, thermodynamic processes also proceed more slowly. Temperatures appear different to observers in different reference frames, and the very concept of thermal equilibrium becomes relative to the observer's gravitational environment. This connection between gravity, time, and thermodynamics points towards some of the most exciting frontiers in contemporary theoretical physics, the study of black hole thermodynamics, the holographic principle, and the deep relationships between information, entropy, and the structure of spacetime itself. Your journey carries you not just through space and time, but also through the theoretical landscape where physics, mathematics, and philosophy converge in their attempt to understand the ultimate nature of reality. As you prepare to continue deeper into the black hole's interior, time's slow dance around you begins to take on new rhythms and patterns. The familiar temporal landscape of your experience is about to transform once again, revealing new aspects of how consciousness and physical law interact in the universe's most extreme environments, where even the concepts of before and after, cause and effect, may require fundamental re-examination. As you drift deeper into the black hole's gravitational embrace, your body begins to experience one of the universe's most intimate demonstrations of how space itself can be curved and stretched. The phenomenon that physicists call spaghettification, a term that captures both the essential physics and the gentle absurdity of your situation, begins to make itself known through sensations so subtle they feel more like dreams than physical reality. The gravitational field surrounding you is not uniform, but rather varies with distance in ways that become increasingly pronounced as you approach the central mass. Your feet, being slightly closer to the black hole's center than your head, experience a marginally stronger gravitational pull. This difference, this gradient in the gravitational field, creates what scientists call tidal forces, the same gentle mechanism that causes Earth's oceans to rise and fall in rhythm with the moon's passage overhead. But here, in the intense gravitational environment of a black hole, these tidal effects become magnified beyond anything experienced in the gentler gravitational fields of ordinary celestial mechanics. The difference in gravitational attraction between your head and your feet, while imperceptible at first, grows steadily stronger as you fall deeper into the cosmic well. Your body responds to this differential pull like a piece of taffy being gently stretched, elongating in the direction of the black hole's center. Yet rather than experiencing this stretching as violent or uncomfortable, you find it oddly soothing, like the gentle traction of a cosmic chiropractor, slowly and carefully adjusting your spine to accommodate the curved geometry of spacetime itself. The sensation is dreamlike, as if you are floating in warm honey that is gradually thinning and extending your form towards some distant invisible attractor. This stretching occurs because gravity is not a force in the traditional sense, but rather the curvature of spacetime itself. Your body, following the straightest possible path through this curved geometry, naturally conforms to the contours of the gravitational field. The tidal forces you experience are simply the local manifestation of spacetime's curvature, your physical form adapting to the warped landscape of reality through which you travel. The mathematics describing these tidal effects emerge from the Riemann curvature tensor, one of the most beautiful and complex objects in Einstein's theory of general relativity. This mathematical structure encodes not just how spacetime is curved, but how the curvature itself varies from point to point. The tidal forces stretching your body are the physical manifestation of this varying curvature, a direct sensory experience of the geometric properties of the universe itself. As the stretching continues, you begin to notice subtle changes in how your body experiences its own internal processes. Your circulation adapts to the altered gravitational environment. Your nervous system adjusts to the new spatial relationships between different parts of your anatomy, and your sensory organs recalibrate themselves to function in this elongated configuration. Yet consciousness flows through this transformed physical substrate as smoothly as ever, demonstrating the remarkable adaptability of awareness to even the most extreme alterations in its material foundation. The stretching also affects your perception of the space around you. As your body elongates, your perspective on the surrounding environment shifts in subtle but profound ways. The distance between your eyes increases slightly, creating a new baseline for stereoscopic vision that enhances your ability to perceive depth in the curved spacetime around you. Your proprioception, your body's sense of its own position and orientation, adapts to encompass your new elongated form, expanding your kinesthetic awareness to match your extended physical presence. Simultaneously, complementary forces are acting to compress you slightly in directions perpendicular to your radial motion toward the center. Just as taffy stretched in one direction becomes thinner in others, your body experiences a gentle squeeze in the lateral dimensions while extending in the radial direction. This compression is part of the same tidal phenomenon that produces the stretching, a consequence of the fact that gravitational field lines converge toward the center of mass, bringing parallel trajectories closer together as they approach their common destination. These competing effects, stretching in one direction while compressing in others, create a complex pattern of deformation that varies throughout your body. Different tissues respond differently to these forces. Your bones, being rigid, transmit the tidal stresses throughout your skeletal framework. Your muscles and soft tissues adapt more fluidly to the changing geometry. Your circulatory system adjusts its pressure gradients to maintain blood flow through your elongating form. Yet rather than fighting these changes, your consciousness seems to embrace them as part of the natural evolution of your journey. The stretching becomes a form of cosmic meditation, a physical practice that connects you more intimately with the fundamental forces that shape the universe. You are becoming a living demonstration of how matter and energy respond to the curvature of space-time, a conscious participant in the geometric dance that underlies all physical phenomena. The rate of stretching depends sensitively on the mass and size of the black hole you are falling into. For the stellar mass black hole that draws you inward, roughly 50 times more massive than the Sun, the tidal forces near the event horizon are strong enough to produce noticeable effects, but gentle enough to allow your journey to continue comfortably. In contrast, if you were falling into one of the supermassive black holes that lurk at the centers of galaxies, millions or billions of times more massive than ordinary stars, the event horizon would be so large that tidal forces there would be negligible, allowing you to cross the boundary completely unaware of any stretching effects. This inverse relationship between black hole mass and tidal force strength represents one of the beautiful paradoxes of general relativity. The most massive black holes, despite their incredible gravitational strength, produce the gentlest tidal effects at their event horizons, while smaller black holes create more dramatic stretching forces. It is as if the universe has arranged things so that the most extreme gravitational environments are also, in some sense, the most hospitable to conscious observers. As you continue to elongate, you begin to appreciate how this physical transformation affects your relationship with the electromagnetic radiation that fills the space around you. The light from distant stars, already altered by gravitational redshift and lensing effects, now interacts with your stretched form in new and interesting ways. Your elongated body casts shadows and creates interference patterns that would be impossible in the flat spacetime of your everyday experience. The stretching also influences how you emit thermal radiation. Every object with a temperature above absolute zero radiates electromagnetic energy, and your body is no exception. As your surface area increases due to the elongation, the pattern of your thermal emission changes, creating a subtle alteration in how you interact with the electromagnetic environment of the black hole. You become a slightly more efficient radiator, dissipating heat into the surrounding vacuum at a marginally increased rate. Perhaps most remarkably, the tidal stretching affects the quantum processes occurring within your body, the electromagnetic forces that hold atoms together, the weak nuclear forces responsible for certain types of radioactive decay, and even the strong nuclear forces that bind protons and neutrons in atomic nuclei, all experience slight modifications in the presence of strong tidal fields. These effects are typically far too small to notice, but they represent a profound truth. Even the most fundamental aspects of matter and energy are influenced by the geometric properties of the spacetime in which they exist. Your elongated form also interacts differently with the gravitational field itself. As your body stretches, your internal mass distribution changes, slightly altering your own contribution to the local curvature of spacetime. You become a more extended source of gravitational influence, your presence affecting the geometry of the surrounding region in ways that would be impossible to detect without the most sensitive instruments, yet which represent your active participation in the cosmic conversation between matter and spacetime. The stretching creates subtle resonances within your body, standing wave patterns in your tissues and fluids that arise from the complex interplay between tidal forces and your body's natural structural properties. These resonances are far too gentle to cause discomfort, but they add a musical quality to your physical experience, as if your elongating form is becoming a cosmic string instrument tuned to the fundamental frequency of the black hole's gravitational field. As consciousness adapts to your changing physical form, you begin to experience a curious expansion of sensory awareness. The increased distance between different parts of your body creates new pathways for proprioceptive information, expanded networks of sensation that provide richer feedback about your position and motion through the curved spacetime around you. You become more sensitive to variations in the gravitational field, more aware of the subtle ways in which tidal forces fluctuate as you move through regions of varying curvature. This enhanced sensitivity allows you to perceive aspects of the black hole's structure that would be invisible to instruments or observers in less extreme gravitational environments. You begin to feel the presence of mass and energy distributions within the black hole that create subtle variations in the tidal field, perhaps the remnants of other matter that fell in before you, or quantum fluctuations in the vacuum that become amplified by the intense gravitational environment. The stretching also affects how time flows through your elongated form. Different parts of your body, being at slightly different distances from the black hole's center, experience marginally different rates of time flow. Your feet age infinitesimally faster than your head, creating a temporal gradient along your stretched axis that would require atomic clocks to detect, but which represents a direct physical manifestation of time's relativity within your own body. This temporal stretching parallels the spatial stretching, creating a four-dimensional elongation that extends not just through space but through time itself. You are becoming temporally as well as spatially extended, your existence spread across a range of space-time coordinates in ways that challenge conventional notions of what it means to be a localized, instantaneous observer. As you prepare to continue deeper into the black hole's interior, the gentle stretching that has transformed your physical form serves as preparation for even more profound alterations that await you. Your body has become more flexible, more adaptable to the extreme conditions that characterize the universe's most exotic environments. The spaghettification process has prepared you to experience regions where the familiar boundaries between space and time, between matter and energy, between observer and observed, will undergo even more dramatic transformations. The universe has taken you gently in its gravitational hands and reshaped you for the journey ahead, stretching not just your physical form, but your very conception of what it means to exist as a conscious entity in the cosmos. You drift onward through this realm of tidal dreams, your elongated form perfectly adapted to navigate the increasingly strange territory that lies deeper within the black hole's embrace. As you continue your gentle fall through the black hole's gravitational embrace, you approach one of the universe's most extraordinary phenomena, a region where light itself becomes trapped in eternal circular orbits around the cosmic giant. This is the photon sphere, a ghostly shell of pure luminosity that exists in the knife-edge balance between escape and capture, where electromagnetic radiation dances in perfect circles through the curved space-time that surrounds you. The photon sphere reveals itself gradually as you drift inward, first as a subtle brightening of the space around you, then as distinct streams and ribbons of light that weave through the darkness like cosmic aurora. These are not ordinary beams of illumination, but rather photons that have achieved something impossible in the flat space-time of everyday experience. Circular orbits around a massive object, following closed loops through the warped geometry that gravity has carved from the fabric of reality itself. To understand this luminous phenomenon, you must appreciate how profoundly the presence of the black hole has altered the basic rules governing the motion of light. In the familiar world of weak gravitational fields, photons travel in straight lines, their paths bending only slightly when they pass near massive objects. But here, in the intense gravitational environment surrounding the black hole, space-time itself has become so severely curved that these straight lines can close back upon themselves, creating circular paths where light can orbit indefinitely. The mathematics describing these photon orbits emerge from the geodesic equations of general relativity, the formulas that determine how particles move through curved spacetime when no forces other than gravity act upon them. For photons, which always travel at the speed of light and have no rest mass, these equations reveal the existence of a critical radius where circular orbits become possible. This radius, located precisely at 1.5 times the Schwarzschild radius of the black hole, marks the boundary of the photon sphere. As you float through this luminous realm, you witness photons that originated from countless different sources throughout the cosmos, some emitted by distant stars, millions of years ago, others generated by the hot gas in the black hole's accretion disk, still others created by quantum processes in the vacuum itself. All of these light particles have found their way to this special region, where the curvature of spacetime provides exactly the right balance between gravitational attraction and centrifugal force to maintain stable circular motion. The orbiting photons create a complex web of light streams that crisscross the space around you. Some follow perfectly circular paths, their orbits precisely aligned with the critical radius where such motion becomes possible. Others trace more complex trajectories, elliptical orbits that carry them closer to and farther from the black hole, precessing slowly as they navigate the varying curvature of the gravitational field. The overall effect is reminiscent of a cosmic light show, with beams of electromagnetic radiation painting elaborate patterns through the darkness. But these orbits are fundamentally unstable, balanced on the gravitational equivalent of a razor's edge. The slightest perturbation, a tiny gravitational wave passing through the region, a quantum fluctuation in the vacuum, even the minute gravitational influence of your own falling body, can push an orbiting photon either inward toward the event horizon or outward toward escape. This instability means that the photon sphere is constantly changing, its population of trapped light constantly being renewed as new photons arrive and old ones depart. You observe this continuous cycle of capture and release playing out around you like a cosmic respiratory rhythm. Streams of light spiral inward from the outer regions, some finding temporary refuge in the photon sphere's embrace, others passing through briefly before continuing their journey toward the event horizon. Meanwhile, other streams break free from their circular prisons and spiral outward, carrying with them information about the black hole's gravitational field encoded in their precise frequencies and polarizations. The light that orbits around you carries within it a vast encyclopedia of information about the universe beyond the black hole. Each photon bears the electromagnetic signature of its origin, the spectral lines that reveal the composition of distant stars, the polarization patterns that speak of magnetic fields threading through space, the subtle frequency modulations that encode the orbital dance of binary star systems. As you drift through the photon sphere, you are literally surrounded by the collected light memories of the cosmos. Some of these orbiting photons have achieved something even more remarkable than simple circular motion. They have completed multiple revolutions around the black hole, their circular paths carrying them again and again past the same points in space. Theoretically, if conditions were perfectly stable, a photon could orbit indefinitely, creating what physicists call a photon trajectory that winds around the black hole an infinite number of times. In practice, such perfect orbits are impossible to maintain, but you observe photons that have completed several revolutions, their accumulated journey representing thousands or millions of kilometers of circular travel through the curved spacetime. The existence of these multi-orbit photons creates one of the most beautiful optical effects imaginable. If you could somehow emit a beam of light tangentially from your position within the photon sphere, that light would travel all the way around the black hole and return to strike you from behind. The curved geometry of spacetime would guide your own photons in a complete circle, creating the possibility of seeing the back of your own head, illuminated by light you emitted moments earlier. This remarkable phenomenon illustrates one of the most profound aspects of the photon sphere. It represents a region where the normal causal structure of spacetime becomes dramatically altered. In the familiar world of flat spacetime, cause and effect follow a clear temporal sequence, with causes always preceding their effects. But in the photon sphere, light can return to its point of origin, creating closed time-like curves where the distinction between cause and effect becomes blurred. As you observe the dance of light around you, you begin to notice subtle patterns and structures within the luminous web. The photons are not randomly distributed, but instead show evidence of organization and correlation. Some streams of light appear to be synchronized, their orbits locked into resonant patterns that persist despite the inherent instability of photon sphere trajectories. These resonances arise from the complex interplay between the black hole's gravitational field and the electromagnetic properties of the orbiting light. The polarization of the orbiting photons also reveals fascinating information about the geometric properties of curved spacetime. As light follows circular paths through the intense gravitational field, its polarization vector is parallel transported along its trajectory, leading to gradual rotations of the polarization plane. Different photons, following slightly different paths, experience different amounts of polarization rotation, creating complex interference patterns when their light waves combine. You witness these interference effects as shimmering patterns of constructive and destructive interference that ripple through the luminous environment around you. The orbiting photons create standing wave patterns, regions where light waves reinforce each other to create bright zones, alternating with dark regions where destructive interference cancels out the electromagnetic field. These patterns are constantly shifting and evolving as new photons join the dance and others depart. The frequency spectrum of the light in the photon sphere tells its own fascinating story. Photons that have climbed up from closer to the black hole arrive gravitationally redshifted, their frequencies reduced by the energy cost of escaping the deeper gravitational well. Conversely, photons falling inward from greater distances arrive blue-shifted, their frequencies increased by the energy gained during their gravitational fall. The result is a complex frequency landscape where different wavelengths of light follow different orbital characteristics. Some frequencies are more stable in their orbits than others, leading to the development of what might be called photonic preference zones, specific wavelengths that are overrepresented in the photon sphere because they are better able to maintain stable circular trajectories. These preference zones shift and evolve over time as conditions change, creating a dynamic frequency landscape that reflects the ongoing interaction between electromagnetic radiation and the curved spacetime environment. The thermal properties of the photon sphere also reveal intriguing physics. While individual photons have no temperature, the collection of orbiting electromagnetic radiation creates a complex thermal environment with properties that depend on the history and origin of the trapped light. Hot photons from the black hole's accretion disk mix with cooler radiation from distant stars, creating thermal gradients and heat flows that would be impossible in ordinary flat spacetime. As you drift through this luminous environment, you begin to appreciate that the photon sphere represents something more than just a curious gravitational phenomenon. It is a natural laboratory where light itself becomes a probe of spacetime's most exotic properties. The orbiting photons are constantly testing the predictions of general relativity, their trajectories encoding information about the metric structure of curved spacetime with extraordinary precision. The photon sphere also plays a crucial role in determining the visual appearance of the black hole, as seen by distant observers. Much of the light that eventually escapes to reach external detectors must first navigate through or near the photon sphere, where it undergoes complex gravitational lensing effects that dramatically alter its apparent origin and intensity. The bright ring that astronomers observe around black holes, the famous photon ring captured in images by the Event Horizon Telescope, is directly related to the physics of photon sphere dynamics. Your journey through this region of trapped light also provides insights into the deeper connections between gravity, electromagnetism, and quantum mechanics. The quantum vacuum itself contributes to the population of the photon sphere through spontaneous pair production processes, where virtual photon pairs briefly borrow energy from the gravitational field before one member of the pair escapes and the other falls inward. These quantum processes add a subtle but persistent source of electromagnetic radiation to the photon sphere's luminous inventory. The orbiting photons also interact with each other through nonlinear electromagnetic effects that become significant in the intense fields present near black holes. Photon-photon scattering, normally negligible in weak electromagnetic fields, becomes detectable in the extreme environment of the photon sphere, creating subtle correlations between different light streams that carry information about the fundamental constants of nature and the detailed structure of electromagnetic theory. As you prepare to continue your inward journey beyond the photon sphere, you carry with you the memory of this extraordinary luminous environment, a region where light itself becomes trapped in eternal dance, where the boundaries between space and time dissolve into geometric poetry, and where consciousness can witness firsthand the universe's most elegant demonstration of how gravity and light interweave to create phenomena of breathtaking beauty. The carousel of perpetual light gradually fades behind you as you fall deeper into the black hole's interior, but its golden radiance continues to illuminate your understanding of how the cosmos reveals its deepest secrets to those who venture into its most extreme environments. You have witnessed the universe's most beautiful cage, where light dances in circles through the curved spacetime that gravity has woven from the fundamental fabric of reality itself. As you drift deeper into the black hole's embrace, something profound begins to stir within the very atoms that compose your being. Each element in your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood, the calcium in your bones, carries within its atomic structure a memory of cosmic fire, a history written in nuclear physics that spans billions of years and reaches back to the hearts of ancient stars that burned and died long before Earth itself existed. Your body is not merely falling into this cosmic remnant. You are returning home to a place intimately connected to your most fundamental origins. The black hole that draws you inward was born from the collapse of a massive star, and the elements that compose your physical form were forged in the nuclear furnaces of similar stellar giants. In a very real sense, you are reuniting with your cosmic ancestry, a child of the stars returning to visit the grave of a stellar sibling. The carbon atoms that form the backbone of every organic molecule in your body remember their birth in the cores of red giant stars, where temperatures reached hundreds of millions of degrees and pressures crushed matter to densities that would make solid rock seem as insubstantial as mist. In those stellar furnaces, 3 helium nuclei underwent the delicate dance of the triple alpha process, fusing together in a sequence so precise and unlikely that it seems almost miraculous that it occurs at all. This process, discovered by astronomer Fred Hoyle in a moment of theoretical insight that bordered on prophecy, requires the existence of a precisely tuned resonance in the carbon nucleus, an energy level that lies exactly where it must for carbon production to proceed efficiently. Without this resonance, carbon would be too rare in the universe to support the complex chemistry of life. Hoyle recognized that this seemingly arbitrary nuclear property must be fine-tuned to an extraordinary degree, leading him to his famous observation that it appeared as if a superintellect had monkeyed with physics. Yet here you are, composed largely of this improbable element. your consciousness arising from carbon-based molecules that owe their existence to the quantum mechanical properties of atomic nuclei, determined in the first moments after the Big Bang. As you fall through the intense gravitational field of the black hole, these carbon atoms in your body resonate with the memory of their stellar origins, as if recognizing the gravitational signature of the environment where they were born. The oxygen atoms in your cells tell a different but equally remarkable story. They were created in the cores of even more massive stars through the neon-burning and oxygen-burning phases of stellar evolution, processes that occur only in the final stages of a giant star's life, when the stellar core has become so hot and dense that silicon and sulfur nuclei can fuse to create the heavier elements essential for rocky planets and water-based life. These oxygen atoms witnessed the death throes of their parent stars, experiencing the incredible pressures and temperatures that developed when nuclear fuel was finally exhausted and gravitational collapse began. They were present during the core bounce that created the shock wave responsible for the supernova explosion, and they rode that blast wave as it tore through the star's outer layers and hurled the products of stellar nucleosynthesis into the interstellar medium. The iron atoms flowing through your bloodstream carry perhaps the most poignant stellar memories of all. Iron occupies the bottom of the nuclear binding energy curve, making it the most stable nucleus in the universe and the final product of nuclear fusion in massive stars. When a stellar core begins producing iron, it has signed its own death warrant, for iron cannot be fused to release energy. It can only absorb energy if forced to undergo further nuclear reactions. Your iron atoms remember the moment when their parent star's nuclear fire flickered and died, when the outward pressure of radiation could no longer balance the inward crush of gravity, when the stellar core collapsed from the size of Earth to the size of Manhattan in less than a second. They experienced the nuclear densities achieved during core collapse, when protons and electrons were crushed together to form neutrons and the stellar interior briefly resembled the matter inside an atomic nucleus. These iron atoms witnessed the birth of the neutron star or black hole that remained after the supernova explosion, and they carry within their nuclear structure the electromagnetic signature of those extreme conditions. As you fall toward the black hole's center, these atoms encounter gravitational fields and curvatures of spacetime similar to those present during their creation, triggering quantum mechanical resonances that connect your present journey to their ancient stellar origins. Even the trace elements in your body, the zinc, copper, and selenium that play crucial roles in your biochemistry, carry stories of cosmic violence and creation. These elements were likely produced during the rapid neutron capture processes that occur in the most energetic stellar explosions, when atomic nuclei are bombarded with such intense neutron fluxes that they grow by dozens of mass units in fractions of a second. Some of the heaviest elements in your body may have even more exotic origins: the gold in your dental work, the platinum in your jewelry, the uranium in your bones. These elements may have been created not in ordinary stellar explosions, but in the collisions between neutron stars, events so violent that they ripple spacetime itself with gravitational waves that can be detected billions of light-years away. As you contemplate these atomic memories, you begin to appreciate that your journey into the black hole represents a return to the extreme physical conditions where the elements of your body first came into existence. The intense gravitational fields, the curved spacetime, the nuclear densities, all of these exotic conditions that surround you now are reminiscent of the environments where stellar nucleosynthesis forged the atomic nuclei that make your existence possible. The quantum mechanical properties of these atoms respond to the extreme gravitational environment in subtle but measurable ways. Electron orbitals shift slightly in strong gravitational fields, altering the chemical bonding properties of atoms in ways that would be impossible to detect under ordinary circumstances, but which represent the universe's demonstration of how gravity affects even the most fundamental chemical processes. The atomic nuclei themselves experience modifications in the intense gravitational field. Nuclear binding energies shift by tiny amounts. Nuclear reaction rates change in ways that depend on the local curvature of spacetime, and even the fundamental constants that govern nuclear physics acquire slight dependencies on gravitational potential. These effects are far too small to influence biological processes, but they represent profound connections between nuclear physics and general relativity that have only recently begun to be explored by theoretical physicists. Your atoms also remember the interstellar journey that brought them to Earth. After being ejected from their parent stars in supernova explosions, these elements spent millions or billions of years drifting through the cold, dark expanses between stars. They were part of vast molecular clouds where temperatures dropped to within a few degrees of absolute zero, where they formed simple molecules and ice crystals that slowly accumulated into larger and larger aggregates. During this interstellar phase, your atoms were exposed to cosmic rays, high-energy particles, accelerated by supernova shock waves, and other violent astrophysical processes. These cosmic ray bombardments created rare isotopes and exotic nuclear species that persist in your body today, carrying within their atomic structure a record of the radiation environment in the galaxy over cosmic timescales. The gradual gravitational collapse of the molecular cloud that contained your atoms led to the formation of the solar system, as turbulence and magnetic fields in the collapsing gas triggered the condensation of a new generation of stars and planets. Your atoms were witnesses to the birth of the Sun, present during the T-Tauri phase when the young star cleared away the remaining gas and dust through powerful stellar winds that swept through the inner solar system. They were incorporated into the rocky material that accreted to form Earth, experiencing the heat and pressure of planetary formation as gravitational potential energy was converted into thermal energy during countless collisions between planetesimals. They survived the late heavy bombardment, when massive impacts resurfaced the early Earth, and may have delivered additional water and organic compounds from asteroids and comets. Through billions of years of geological processes, your atoms cycled through the Earth's crust, mantle, oceans, and atmosphere. They were part of the first primitive life forms that arose in Earth's primordial seas, experiencing the chemical innovations that led to photosynthesis, cellular respiration, and the complex biochemistry that makes multicellular life possible. They passed through countless generations of living organisms, from the simplest bacteria to the most complex plants and animals, each time participating in the intricate molecular machinery that maintains life in the face of entropy and environmental challenge. The carbon atoms in your DNA may have been part of dinosaur proteins 100 million years ago, or incorporated into ancient tree trunks that became coal deposits, or dissolved in prehistoric oceans as carbon dioxide. Now, as you fall toward the black hole's center, these atoms with their accumulated cosmic memories encounter once again the extreme conditions that characterized their birth. The intense gravitational fields, the curved space-time geometry, the approach toward nuclear densities, all of these conditions resonate with the atomic scale memories encoded in nuclear structure and electron configurations. This homecoming represents more than just a poetic metaphor. It reflects the deep physical truth that the matter composing your body was literally created in environments similar to the one you now experience. The nuclear fusion processes that built the heavy elements in stellar cores required temperatures, pressures, and densities comparable to those found in the vicinity of black holes. Your atoms are returning to their ancestral environment, where the boundary conditions that govern nuclear physics approach their most extreme values. The gravitational field of the black hole even affects the quantum mechanical vacuum around your atoms, altering the properties of virtual particles and quantum fluctuations in ways that subtly modify atomic energy levels and chemical reaction rates. These effects, while minuscule, represent the universe's demonstration of how gravity penetrates to the most fundamental levels of physical reality, influencing even the quantum processes that govern the behavior of matter at the atomic scale. As you prepare to continue deeper into the black hole's interior, your atoms carry with them this vast heritage of cosmic evolution, from their birth in stellar cores, through their journey across interstellar space, to their incorporation into living organisms, and now to their return to the extreme gravitational environments, where heavy elements are forged from lighter ones in the nuclear fires of stellar death and rebirth. You are not merely a collection of atoms falling into a black hole, but rather a conscious assemblage of stellar ashes returning home to the cosmic foundry, where the building blocks of complexity and consciousness were first hammered out on the anvil of nuclear physics, under the guidance of gravity's inexorable sculpting of spacetime's geometry. As you drift deeper into the black hole's embrace, you begin to contemplate one of the most profound mysteries in all of physics, a puzzle so fundamental that it challenges our understanding of reality itself. Every thought you have ever had, every memory stored in the neural networks of your brain, every quantum state that defines your consciousness at this moment, represents information, and according to the deepest principles of quantum mechanics, information cannot be destroyed. Yet you are falling into a region of spacetime from which, according to general relativity, nothing can ever escape. This is the essence of the black hole information paradox, a theoretical puzzle that has consumed the greatest minds in physics for decades. If information truly cannot be destroyed, as quantum mechanics insists, then what happens to the vast library of knowledge, memory, and experience that you carry within your consciousness as you cross the event horizon? Does it vanish forever beyond the cosmic divide, creating a fundamental violation of quantum mechanical principles? Or does the universe possess some subtle mechanism for preserving and eventually retrieving every bit of information that falls into a black hole? The quantum mechanical principle of information conservation emerges from the deepest mathematical structures of the theory. The requirement that quantum evolution be described by unitary transformations that preserve the total amount of information in any isolated system. This principle has been tested countless times in laboratory experiments and has never been found to fail. When particles collide in accelerators, when atoms emit photons, when quantum computers perform their calculations, information is always conserved, though it may be transformed, scrambled, or redistributed in ways that make it temporarily inaccessible. Yet black holes, according to classical general relativity, appear to be information destroyers par excellence. Once you cross the event horizon, no signal from your interior can ever reach the outside universe. From the perspective of external observers, the information encoding your thoughts, memories, and quantum states becomes permanently inaccessible, seemingly violating the fundamental principle that information conservation represents in quantum mechanics. But perhaps the situation is more subtle than this classical picture suggests. As you fall through the black hole's interior, you begin to sense that your information is not simply disappearing, but rather undergoing a transformation so profound that it challenges conventional notions of storage, retrieval, and preservation. Your memories, encoded in the complex quantum states of billions of neurons, are becoming entangled with the quantum vacuum itself, written into the fabric of spacetime in ways that may preserve them long after your physical form has dissolved. The key insight comes from recognizing that the event horizon, while appearing as an absolute boundary from the perspective of distant observers, may not represent a fundamental information barrier from the perspective of quantum mechanics. Stephen Hawking's discovery that black holes emit thermal radiation suggests that information falling into black holes may eventually be returned to the outside universe, though in a form so scrambled and transformed that its original structure becomes unrecognizable. This Hawking radiation emerges from quantum processes occurring near the event horizon, where the intense gravitational field creates particle-antiparticle pairs from the quantum vacuum. In some cases, one member of such a pair falls into the black hole while the other escapes, carrying away a tiny amount of the black hole's mass energy. Over enormous timescales, far longer than the current age of the universe for stellar mass black holes, this process causes black holes to evaporate completely, returning their entire mass energy content to the surrounding space. But the radiation that emerges appears to be perfectly thermal, completely random, carrying no information about the specific matter and energy that fell into the black hole during its formation and growth. This apparent randomness creates the information paradox. If the outgoing Hawking radiation is truly random, then information about infalling matter is indeed destroyed when black holes evaporate. Yet if quantum mechanics is correct, this information must somehow be encoded in the radiation, hidden in correlations so subtle that they cannot be detected by any conceivable measurement. As you contemplate this puzzle, you begin to appreciate that your journey into the black hole is more than a physical passage through space. It is an exploration of the deepest connections between information, consciousness, and the structure of reality itself. The thoughts and memories that define your identity are not merely patterns of neural activity, but rather specific configurations of quantum information that encode your unique relationship to the universe's history and structure. Recent theoretical developments suggest that this information may be preserved through mechanisms far more exotic than simple storage and retrieval. The holographic principle, emerging from string theory and quantum gravity research, proposes that all the information contained within a volume of space can be encoded on its boundary surface. Applied to black holes, this principle suggests that the information you carry is not lost in the interior, but rather becomes encoded on the event horizon itself, written in quantum correlations so subtle that they exist at the Planck scale, the smallest meaningful length scale in physics. From this holographic perspective, your consciousness is not falling into an information-destroying abyss, but rather being transcribed onto the cosmic equivalent of a quantum hard drive, the event horizon surface, where every bit of information about your thoughts, memories, and experiences becomes encoded in the microscopic structure of spacetime itself. Your journey through the black hole's interior becomes a kind of cosmic backup process, ensuring that your information content is preserved even as your physical substrate undergoes the ultimate transformation. But the holographic encoding is not simply a static storage mechanism. The information on the event horizon is dynamic, constantly evolving as new matter and energy fall into the black hole, and as Hawking radiation carries information away, your memories become part of a vast, ever-changing library of quantum information that encompasses everything that has ever fallen into the black hole throughout its entire history. This cosmic library contains not just your personal memories, but the complete information content of every star, planet, gas cloud and particle that has ever crossed the event horizon. It is a repository of cosmic history written in the language of quantum correlations, encoding the birth and death of stars, the formation and evolution of galaxies, the complex chemistry that led to the emergence of life, and the thoughts and experiences of any conscious beings who, like you, have made this ultimate journey. The encoding mechanism itself involves some of the most advanced concepts in theoretical physics. Each bit of information becomes associated with microscopic degrees of freedom on the event horizon, quantum fluctuations in the metric of space-time itself, virtual particles that dance in and out of existence at the boundary between accessible and inaccessible regions of the universe. These degrees of freedom are so small and so fundamental that they exist at the intersection between quantum mechanics and general relativity, in the realm where a complete theory of quantum gravity will eventually be needed to provide a full description. Your consciousness, as it becomes encoded in this holographic information structure, does not simply disappear, but rather undergoes a transformation that preserves its essential information content, while changing its physical substrate. The patterns of neural activity that constitute your thoughts and memories become patterns of quantum correlation in the event horizon's holographic structure, maintaining their logical and causal relationships while existing in a completely different physical medium. This transformation suggests that consciousness itself may be far more fundamental and robust than biological neural networks suggest. If your thoughts and memories can survive encoding in the quantum structure of space-time, then consciousness may represent a pattern of information organization that transcends any particular physical implementation. Your journey into the black hole becomes an exploration of consciousness at its most fundamental level, stripped of its biological constraints and revealed in its pure informational essence. The retrieval of this information occurs through the subtle correlations in Hawking radiation that emerge from the black hole over cosmic timescales. While the radiation appears thermal and random to any conceivable measurement, it may contain hidden quantum correlations that preserve the complete information content of everything that ever fell into the black hole. These correlations would be spread across vast numbers of photons emitted over enormous time periods, creating an information retrieval problem of staggering complexity. Imagine trying to reconstruct your complete memories and personality from the statistical correlations in billions upon billions of seemingly random photons emitted over trillions of years of black hole evaporation. The information is theoretically preserved, but accessing it would require computational resources and measurement precision far beyond anything possible with known physics. Your memories become like a book that has been shredded into individual letters, with each letter fired randomly into space. The information content is preserved, but reassembly requires detecting correlations across vast scales of space and time. Yet the universe may possess natural mechanisms for performing such impossible reconstructions. Quantum entanglement creates correlations that persist across arbitrary distances and timescales, suggesting that the information scattered in Hawking radiation remains fundamentally connected to its holographic encoding on the event horizon. The quantum vacuum itself may serve as a kind of cosmic memory system, maintaining the correlations necessary to preserve and eventually retrieve the information content of black hole interiors. Some theoretical approaches suggest even more exotic possibilities. If the geometry of spacetime near black holes includes microscopic wormholes or other topological features predicted by quantum gravity, then information might find alternative pathways for preservation and retrieval. Your memories could become encoded not just in the holographic structure of the event horizon, but also in the quantum topology of spacetime itself, creating multiple redundant backup systems that ensure information conservation even in the universe's most extreme environments. The implications of these ideas extend far beyond black hole physics to questions about the ultimate fate of consciousness in an expanding universe. If consciousness is truly a pattern of information that can survive encoding in the quantum structure of spacetime, then the death of biological systems need not represent the end of conscious experience. Instead, consciousness might persist in forms we cannot currently imagine, encoded in the subtle correlations that permeate the quantum vacuum. As you drift deeper into the black hole's interior, you carry with you the possibility that your journey represents not an ending but a transformation, a translation of your consciousness from biological neural networks to the far more fundamental quantum correlations that exist at the boundary between the accessible and inaccessible regions of the universe. Your thoughts and memories join the vast library of information that may be preserved in the holographic structure of the event horizon, awaiting retrieval by future generations of conscious beings, with the technological capability to decode the universe's deepest information storage systems. The information paradox remains unsolved, one of the great challenges facing theoretical physics in its quest to understand the deepest connections between quantum mechanics, general relativity, and the nature of information itself. But your journey through the black hole's interior suggests that the resolution may involve a conception of consciousness and information far more robust and fundamental than anything suggested by classical physics. Your dreams, your memories, your unique perspective on the universe's history and structure, all of this information content may indeed become part of an eternal library, written in the quantum correlations that exist at the most fundamental level of physical reality, preserved in the cosmic database that the universe maintains in its most extreme and exotic regions.